So you may be wondering, why didn't I apply the equilibrium equation to member BC like I did to the joint, like I did to member AB? I mean, aren't we moving in the clockwise manner through the members? That is, we started moving from member AB, then we went to joint B. Are we not supposed to apply it to member BC? Well, that's a brilliant question, a very smart and intelligent person. So, C, this is BC. Why are we not applying it? Now, you notice that at C, I mean, there's no support here. That is, there's no reaction there. So there's nothing for us to find again in BC because we have used the equilibrium equation on joint B to get all that we needed on member B. I mean, looking at the equilibrium equation, looking at the free body diagram, I'm currently on this view. Looking at the free body diagram of this, we use the equilibrium equation on joint B to get BYBC, to get BXBC, which was 0, and BYBC. So apart from BYBC, there's nothing else on the member BC that we need again. So there's nothing else on that member BC that we need again. So there's no point in applying equilibrium equation to member BC. Applying equilibrium equation will just verify the fact that you are correct already. What do I mean? Let us apply the equilibrium equation to member BC. You see what I mean? Summation Fy is equal to 0. So to be, the way I like to think of it is upward is equal to downward. So BYBC is equals to 1.6 times 15. That gives me 10. A minute. Something. It's 24. So yeah. So I was where was I? 1.6 times 15. So 24. So BYBC is 24. It's just to confirm. Can you see? It's just to confirm that our BYBC is correct. We already know that BYBC from equilibrium equation from the joint is 24. So now we can proceed. We can move to the shear force, the bending moment computations. Now, I will be drawing the structure again. You can copy it. A minute. I want to copy this structure, so I won't have to draw everything. Okay, I'll paste it here. So once again, it's not even the structure we need. We need the decomposed part of the structure to draw the shear force and bending moments. Why? Why do we need the decomposed part of the structure to get the shear force and bending moments? Sorry, guys. Sorry. We need this because we are going to, when we draw our shear force and bending moments, we are drawing for individual members. Okay, we are saying that what is the shear force in this column? What is the bending moment in this column? So separately, we can now say, okay, what is the bending moment in this beam? What is shear force in this beam? So that is one of the reasons why we can split, why we split our members and split which split the shuffles and bending moments for each members. So splitting it, well, like it is here, which is what we're currently seeing, we can withdraw it. Withdrawing it, we found that equilibrium equation gave us, okay, this is A, this is A, an equilibrium equation, when we applied it to the structure, gave us AY as 24. It gave us AX in this direction as 25. And it gave us a moment, this direction of 430. So when we apply the equilibrium equation to this member to get the moments, to get the internal loads at B, we found that a force will be acting in this direction at that end, which was 24, and we saw that there won't be no 25, there won't be any horizontal force, just a vertical force. And now 180. So let me erase this and draw it in a more orderly version. But let's just take it as a straight member. I'm sorry. I'll just take it as a straight member. So normally in drawing shear force and in solving shear force and bending moment questions, we're used to our structures being horizontal. I'm sorry. We're used to our structures being horizontal. But now, at least when we're used to our structures being horizontal, we take this as the y direction and we take this as the x direction. Exactly. So what we're doing now, maybe when we are analyzing, for instance, member AB, what we are doing now is that it's not different at all, in the sense that these are vertical member and this is the x direction. Think of it like that. And this is the y direction. You just have to tilt your face in that manner. You just have to tilt your face. So, knowing this, we can see that the orientation doesn't change the steps that we have to take. The steps remains the same. I mean, see the horizontal member wise, so the y direction and the x direction. So it's just the view that you look, where you look at it. So let's start our shear force computations. Now, to find my shear force, let me first of all use the method of sections, or let me just do the normal way of doing the shear force. So remember that this is my y direction. And this is my x. I remember that in the former one, the horizontal one, the shear force is already, the forces we put in consideration under shear force are always in the y direction. So it means that when we are doing shear force, we are looking at the y direction forces. Do you understand? The forces that are in that direction, basically. So it means that if this is A, this is A, of course, and B. So it means that my shear force at A will be plus 25. I mean, the y direction, so that particular force acting in the y direction, positive. I would like you can, if you don't get it, you can tilt the member, you can make the member horizontal by tilting it in this manner. Then you understand what I'm saying, that, wow, this is actually plus 25. Or you just have to, if you don't want to waste time by redrawing it, you can tilt your neck while viewing this. Tilt your neck this way. Then you understand. You'll see what I'm saying. So, once again, I'm looking in this direction for my shear force. So, because that is the y direction. So plus 25 at A, kilonewtons. Now, if A, B, C, D, let's put this as E. VE will now be plus 25 minus 25. It will now be 0 kilonewtons. And VB will be zero also, because there's no other vertical force in order to change that value, change this value rather. I mean, after here, after this member E, after this point at E, there's no other vertical force, so the shear force just continues at 0. So sorry. The shear force just continues at 0 after E. So 25 minus 25, 0, then in fact it just moves and continues at 0. It drops down. Like 25 brings it up at A. It remains constant. I mean, the purpose, the way to think about shear force and bending moment is that they try, or I would say this in a video coming up later. Let us save this moment for frames. So I will explain shear force better and bending moment in another video later. So VB is equals to 0. So that is it. But of course, for people, for students, your lecturer might not really like this method. He would want you to section. So the way to section and get your mark. I mean, this is proper understanding, but your lecturer's marking scheme might not revolve around this. So, to section, well, first of all, I mean, when we are sectioning, we section between points of discontinuities. So it means that we're going to be sectioning 2 points, two spans rather. Not spans, but two regions. Region 1, region 2. Let's call this X1, X1, and X2. X2, we're going to be sectioning these two. Coming to this guy, coming to this view, to this space, rather. Let me start with sectioning X1. In sectioning X1, once again, this is my member, and this is the section. I've cut X1. I've divided A to E with a knife. I've sectioned it. I've sectioned it. So once again, since it's shear force I'm dealing with, I will just be considering the vertical force for now. So if I section that from here to here, it would be X. And of course, the direction for shear force when you section would be in this manner. So this is 25. So one way to go about sectioning is to apply equilibrium equation to this free body diagram by saying V down, upward is equal to downward. So once again, you should know that this is X and this is Y. So when I say upward is equal to downward, I'm considering the Y direction. So V is equal to 25 when we apply equilibrium equation to this free body diagram. On the video coming up on shear force and bending moment, what it means, you would understand why we are applying equilibrium equations to these free body diagrams. Ordinarily, you can go through another route, which is the normal one where people just bring V from nowhere and say, okay, since this 25 kilonewtons is coming up, maybe we're talking about VA, then at A it will be 25. At B, at X also, because that is we're dealing with X now. So 25, meaning that as long as it has not reached E, the shear force is still 25 kilonewtons. But now let's do when it reaches E. The way to do this is to consider the next discontinuous the next span, the next cut rather, the next section. We do this by saying, okay, 25, 25, and this is the discontinuous point. This is the section X2, X2. Once again, your shear force goes in this direction, Vx. You'll see more on this in the shear force and bending moments video. So sorry, I'll be coughing a lot in this video. I'm so sorry. I'm having cold, and please, I didn't want it to restrict me from releasing videos like this, so I just had to continue. There isn't so much time on my hand because I'm currently in a tight semester. So I hope you understand. I love you guys. So this is the next, this is E, this is A. Now I'm considering the next cut. So applying this equilibrium equation, Vx, applying equilibrium equation to this, X down, plus 25 down, equals to 25. Then Vx is equal to 0. That is, after E to B, our shear force will be 0 kilonewtons. That is just what it is saying, basically. When you have, for this now, we got Vx to be 25 kilonewtons. You'll notice that this 25 kilonewtons is satisfied as long as it doesn't reach E, in the sense that it will go from 0, less than, I think here was 10. The distance of separation was 10. To go from 0 to 10. Notice that I didn't have this. I had this. So that is just before this 25 kilonewton is satisfied up to just before E. Because at E, there's going to be a jump. You get. So also for this, it starts after E. That is after E. Immediately after E, it will be like 0. So we also see that it happens from but please, if you don't understand all this, it's still fine. It's still fine. You're still fine. What I'm just trying to say is that it's still your normal shear force and bending moment, please. But I'm just trying to like be more detailed. But this is just what I've been talking about for this expression now. Using our normal shear force now, where we bring V, we'll now say plus 25 minus 25 VE. It will be 0. That is VA plus equals to plus, and it's still your normal shear force. Please, still your normal shear force. So now, it means that for shear force, VA is equals to plus 25. VE is equals to 0 kilonewtons. VB 0 kilonewtons. Let's have this in mind. So let's do the bending moment now. Don't shear force, let's do bending moments for that same member. Now, remember this is still the member. And we had 180, we had 24, we had 4, 25. So, for moments, it's still the same thing. We just have to find moment at various points, various critical points. A, B, E. P. A, B, E. So, it's still the same thing. It's still the same thing. I'll show you. Once again, looking at this screen, facing the screen, but tilting your neck this way. That is, you're tilting your neck to the left, looking at it once again like that. We say we now do the bending moment. To do this, say that MA is equals to, or let me cut it. Let me do sections. Sectioning this. sectioning x, x, x1, x1, x2, x2. I'll be sectioning it at 2 points. So moving to this space. Now sectioned already. X1, x1, sectioned. So the moment comes like this. So to find the moment for this particular free body diagram that we just sectioned, it will be mx, here, mx. Not even applying, let me rush through this. You can do well to apply the equilibrium equation, you get the same thing, but the convention I normally use when dealing with moments is that anytime this is my beam and my couple, my moment, tries to bring my beam downwards, whether this particular moment, let's say this particular moment tries to bring my beam downwards, maybe it's orientated in this manner, and in this manner it tries to bring my beam downwards, I'll give it a negative sign when I'm doing my bending moment. Similarly, for this is trying to bring my beam downwards, that is, it's trying to make, just trying to make my beam to be bent in that manner, I'll give it minus also. But however, if it's trying to make my beam pull it upward, for this is doing the job, so positive, for this also is doing the job. So using this technique, I can say that mx is equals to, now this guy will bring the beam downwards. If we look at it in the manner that I've been telling us to look at it, it will bring the beam downwards. So I'll be having minus 430, that particular couple, minus 430. This mx is the guy that is here, so no need to, you can use the equilibrium equation, you get the same thing, but like we normally do in shear force, where we just bring the v is equals to, and we calculate our shear force algebraically. That is just like the similar thing I'm doing here. I mean, here I'm dealing with moment, so moment is equals to, I'll start solving algebraically for my moment by applying the convention, which is this that I just showed us. So minus 430. Now, a force can be converted to a moment by multiplying the force by its perpendicular distance. So, but for now, I'm dealing with a distance of x. Because I cut it at any location there. So 25 times x. That 25 will be bringing my beam upward. So plus 25 times x. So mx is equal to minus 430. Once again, plus 25x, don't mind me. But it means that MA will be equal to minus 430 plus 0. I mean 25 times 0. I mean A is 0. A is x at 0. So M is equal to minus 430. Obviously. So now it is only in bending moment that you can maybe you cut. Okay, I'll explain it. MB is equals to. Don't try this thing for shear force, but you can try it from bending moment. It works. So minus 430. I'm coming. I'll show you the thing, but follow along. Before I show you. So 25 times. Now, ME, sorry, I mean ME, not MB. ME is equal to 25 times 250. Okay, I'm checking if I'm on track. In my notes, I will send the notes. But track. Can fast forward it. Okay, I'm on track. So I have minus 180. Okay. Now it remains MB, but it is either to bring this cross section. Remember that the definition when we define shear force and bending moment, it is either we use any of the portions that we have cut to get the shear force and bending moment. That is, it is either I go through this. It's either I cut. Now I'm looking at section X2 now. It's either I cut my beam at X2 here. It's either I use this cut at X2. 25 is there. Five is there. So either I use this cut or I use the other one joining it, which is this cut, which is much shorter. 180, 24. Get what I mean? It's either I use the demarcator, the cutter. It's either I use this part or I use this part. I have to choose one. So I choose the shorter one. So here I go. X2, X2, 24, 180. So once again, this is X direction and this is Y direction. And once again, tilting your neck in this manner such that you see it in an horizontal manner like this. Yes. So I'm sure that everybody is glad I showed them this. But okay, this is it. Now we can now analyze. Since this is cotton, we can, and this is M. We can now say that MX is equal to. Now there's no moment that can come from any force here. Just moment coming from this moment, this couple, which is minus 180 based on our convention. So it means that all moments moving in this span, that is moving from here to here, in this part, since I cut at X. The reason why I'm saying that is because, I mean, I cut at X. So this X, think of it as something that is adjustable. I can adjust my X to any distance as long as it's between B and E. So that is, since I cut in that region, it means that any moment in that region satisfies this equation. So minus 180 constant. So there was something I said that you should not try for shear force, and that's the fact that now see something. You know, I said that we can use we can cut. I mean, when we cut our member, we have two portions. So we can use this portion. So remember that this is the cut part. This is the demarcator, the cut section. So do you know that if I want to get moment at E, I can either cut through here, or I can just cut like in the beginning, which is what we did. And I can just cut like this. Or I could have just even cut. Oh, what am I saying? I'm sorry. So let me come again. This code is a lot. Let me come again. So, to get moment at E, which is something that should be done for only moments, I can cut like this, then apply all these things that I'll be doing to get my moment at E. You know, to give me an equation, then I'll just plug in the value of x at E. Or, which is what I did, I just went through the faster one, I cut here, and I found the moment at E. This should be done only for moments. If you try it for shear force, you won't get your values. That is, to get something in this region, in this particular location, I can cut here or cut here to get it. Why am I saying that? I'm saying this only works as long as what is separating these two cuts is a force, if at all it is moments you are using it for. I mean, moments, yes, is a force. But had it been, it was a moment that was here, a couple. Had it been, it was a couple that was here. And if you are dealing with moments, you cannot try this any longer for moments. You cannot use the demarcator or the section in this guy here or in this guy here to get at E. To get the moment at E. We can't use it anymore. It will only work for shear force now. So that is just the case. So it means that I have MA minus 430 kilonewton meter ME minus 180 kilonewton meter MB minus 180 kilonewton meter. Now, the remaining one, there's something called axial force. Now, looking at the member again. A minute. This is a member. Something there. 25. 24. 24. Blah, blah, blah. So it's mixed up. See? For 13. 25. Now for axial force, the convention is that anything that tries to pull your beam apart is positive, and anything that tries to cause compression is negative. So looking at this, force, I mean, cutting in this place, it means that I would have You understand the portion I will have left. I'm using the smaller portion now. It means that this force is trying to compress my member. So it means that my axial force, let me use Z. Axial force at A will be minus 24. Similarly, coming here to cut and taking just that portion, taking just this portion, this cut portion, you will see that this axial force of 24, I mean, when you take this blue portion, it means that you have neglected the other downward portions. So taking just that portion, you see that it is only 24 that we can consider as axial force also, and it will also cause a compression. So VB is equal to minus 24. You notice that axial forces now deals with the parallel side of the beam, that is the x-axis. X-axis, and remember this was the y-axis. So that is it. Now, member BC now. We don't do shear force and bending moment for joints. Member BC. This is it. So, shear force computation. Now, I love to cut, so oh no, I love to cut my beam, so let's cut our beam. Let's cut it. It shows the lecturer you know what you are doing. I see, of course, this is a UDL, but let me represent my UDL in a better way. Let me represent my UDL in a much better way, but still cutting. So, once again, so, and this was 1.6, and from here to here is x. So normally the way we just do it is that we say shear force is equals to 24, which is at B, minus 1.6x. So this is the equation for shear force along B to C. Along B to C. Because, I mean, we just, the method of cutting basically works when you notice that, okay, this loading type is the same from a particular point to a particular point. But when you see that the loading now change, you will now go and cut it where the loading changes again and apply, do the same, repeat the same process, get the new shear force equation. That shear force equation will be consistent from where you stopped, from where the previous equation stopped working to where the new, when you cut it. Well, we'll explain more of this. I think that as you follow along, as you learn all these things, you would be used to it. And yes, a video is coming up very soon on force and bending moments. So we'll see how all these things relate. But you will see that from all this, you need to make sure your shear force and bending moment is strong. Please and please work on your shear force and bending moment diagrams. Work on your shear force and bending moment speed. Yes. So this is equals to that. Now, of course, we will need this equation. I don't like to normally differentiate my bending moment equation. I mean, when I differentiate my bending moment, I get my shear force, right? I mean, M over EI is equals to Y prime prime. This for bending moment, and this for shear force. Y prime prime prime. So when I differentiate my bending moment, I get my shear force. Sorry, I meant. Wait a minute. Okay, yes, I'm right. So when I differentiate my bending moment, I get my shear force. Yeah. But now, how the purpose of me even saying that is that remember that when we want to find maximum bending moment from the moment equation, that is when we want to find the position of the maximum bending moment, we differentiate that equation we have for moment, that equation of moment we have. We differentiate it. We say dm over dx is equal to 0. What we're basically saying is that we're converting that equation to a shear force equation. And remember that we equate that equation to 0. So it means that we're saying that, okay, guy, give me a position of x that would make my shear force equal to 0. What is the special thing about your shear force being 0? Your shear force being 0 is the place where your moment will be maximum. But I mean, how should I go through all that stress when I have my shear force now? Why can't I just put 0 in my shear force? Exactly. If I can put 0 in my shear force now, I can get my maximum bending moment position. So 0 is equals to 24 minus 1.6 times x. So it means that I would have 1.6x is equals to 24. So it means that my x will be, my maximum bending moment will be at 15.0 meters from B. Why from B? Because I cut it, my direction of computation was in this manner. You can see that I was moving in this manner when computing. I started from B. Do you understand? That is, I'm considering this portion. You know that when you cut it's not even about moving or direction of computation. It's about the portion you use when you want to solve. I use the remaining portion left, which was this guy. I would have been considering this manner. I hope you understand that direction. So, from B. So what is left? Now we have our shear force. Let's do our bending moment. So, looking at this once again. towards the section, and after the section our moment is always orientated in that manner. Like, it's not that it is always, but engineers prefer it to be in that manner. So 1.6, so 24. Once again, we don't need to waste time to apply equilibrium equations. We just need to do our bring out m and form the equation. Once again, this is x from here to here. So 24x, which is positive because it brings the beam upward, minus 180 brings the beams downward, minus this UD here also brings the beam downward, which is 1.6 x squared over 2. Mx is equals to 24x minus just the same thing. Let me not even equal. Let me not try to solve anything. So mx, because we're dealing with x guy. So looking at this now, we can see that okay, we can find our maximum bending moment by putting 15. Remember that we got from shear force that maximum bending moment is 15. So let's find that. But before we even find our maximum bending moment, let's find MB when x is equal to 0. When x is equal to 0, it will be all minus 180. When m is equal to m max, it will be 0 when you put 15 inside this equation. It makes sense because there is no support in that region. So diagrams, the part we have been waiting for. Now, remember that our shear force at A was 25. Our shear force at B was 0, which is equal to the same thing as shear force at C. Oh, sorry. Shear force at C. Yes, which is the same as shear force at B for member AB. And similarly for member AB, our MA was a minute. Our bending moment was minus 430 kilonewton meter. Our ME was equals to our MB, which was equals to minus 180 kilonewton meter. And for A shear force, ZA was equal to ZB, was equal to minus 24. Knowing all this, we can now draw for that particular member, our shear force bending moment. So let's draw 3 lines to represent our shear force bending moment and A shear force, where this is our shear force, the first one, SFD, BMD, A shear force diagram, A shear force diagrams. I think they call it NFD also, but I've forgotten the meaning of the NFD. You can search for it. So all that said, it means that, plus 25. Okay. All that said, a minute. Sorry, I made a mistake. VA, VE. Okay, okay. A mistake. Don't mind me. Don't mind me. That's when you before something. Okay, let's say you have a UDL like this. Let me use this instance. Let's say you have a UDL, and the UDL and there's a point load. No matter what is in this region before the point load, as long as you have a point load, you must do something. You must calculate the shear force just before E. Maybe this is E. You must calculate the shear force just before E and at E. So just before E still gives us 25. But at E, when the action takes place, the jump, so 25. A, E, B. Similarly, bending moment 430 A, then at E, it's moved to 180. I say this is still 430 and 180 also. Minus BMD. And A shear force 24, same 24 constant. So similarly for the horizontal members, draw it for the BMD also, draw it for the AFD. In fact, there's no AFD for the third one. If you notice, there's no horizontal force. So looking and going back to the video, you see that shear force at B for member BC is 24. Then at C, 0. Similarly, we know that for bending moments is 180 at B. If you check the video, and we know that the maximum is here at 0. You see that this 180 is minus 180. Oh, please, is minus 180. This 25 is plus 25. Oh, notice why I'm putting positive. I just remove the sign, then put the magnitude outside. So minus 180. So, but for this now, 0 is the maximum. But how can I join it? Is it like this? Or is it like this? Or is it like this? How? Now, to know how, you need to know something. That your shear force is the slope of your what's the name? Your bending moment. The slope of your your shear force, that is at a point O. Let's say at this point, remember your shear force is the slope of your bending moment. So if your shear force is the slope of your bending moment at various points, so at point B, it means that the slope of my bending moment at point B would be I, because the shear force here is 24. But it now keeps reducing. The shear force keeps reducing. It means that the slope of my bending moment would also reduce. And for slope to reduce, it means that it must tend to 0. So if it increases here, maybe because it's 24, the slope will start reducing. It will start reducing until it becomes 0, a 0 slope. So it will be curved in this manner. in this manner. So please, that is all for it. That is all for the video. Thank you. Thank you so much. Thank you so much.